Okay, in this video, we are going to do some examples of triple integrals. The other integrals that we looked at were called double integrals because there were two of them. These are called triple integrals because there's three of them. And the procedure is very similar. We're going to work from the inside out. So at first, we'll just basically ignore the outer two integrals and just work with the inner integral. And let me just point out that the order of the integrals here has to match up with the order of the differentials, the d stuff here. So notice that we have a z on the inside and we have a dz on the inside. We have a y in the middle, we have the dy in the middle here, and x is on the outside and dx is on the outside there. So what is this? Well, again, as far as z is concerned, x and y are constants. So we can write this as the integral x equals -1 to 3, y equals 0 to 1, x cubed y squared times the integral z equals 0 to 2 z dz dy dx. Okay, now what is this? This is the integral x equals -1 to 3, the integral y equals 0 to 1. I'll write the x cubed y squared Okay, now the antiderivative of z is z squared over 2. And we're going from z is equal to 2, to z is equal to 0 to z is equal to 2. Sorry, I can't seem to make the y the way that I want to. Okay, so this inner integral is the integral from 0 to 2 of z. The antiderivative of z is z squared over 2. We're going from z is equal to 0 to z is equal to 2. So that's 2 squared minus 0 over 2. That's 4 over 2. That's 2. Okay, now we have a double integral. Notice that we do the inner integral. Now we have a double integral, and we completely forget that the inner integral ever existed. Now we just have this double integral to do. So this is going to be the integral from x equals -1 to 3, 2x cubed, and now this inner integral is the integral from y is equal to 0 to 1 y squared dy dx. So the y integral, the integral from y equals 0 to y equals 1 of y squared, that's just 1 cubed. So now this is 2/3 times the integral from x is equal to -1 to x is equal to 3, x cubed dx. This is 2/3. Okay, the antiderivative of x cubed is 1/4 x to the power of 4. So this is 1 over 4. So this is 2/3 times 1/4. And now the x to the power of 4 going from -1 to 3. This is 3 to the power of 4 minus -1 to the power of 4, so that's -1. And this is, so 3 to the power of 4. 3 cubed is 27, so 27 times 3 is going to be 75, and here comes my son. That's 81. So this is 2 times 81, so that's 162 over 12. And of course, this can be simplified, but I will let you do that on your own. And of course, that's wrong. 3 to the power of 4 is 81. 81 minus 1 is 80. 2 times 80 is 160. So this is 160 over 12. Let me just erase this to make it a little more clear. Okay, now let's move on to the next example. Again, similar to the problems above, this looks very similar, except the integrand is the same. The limits on the integrals are the same. We're just doing the integral in a different order. So this is going to be the integral y equals 0 to 1. The integral z equals 0 to 2. Now the inner integral is going to be an x integral. So I'm going to go on ahead and factor out the y squared and the z. Again, because as far as x is concerned, y and z are constants. So this is the integral x is equal to minus 1 to 3 x cubed dx. And then on the outside, we'll have dz dy. And again, just pay attention, the y is on the outside. Well, this is a typo. I told you to be careful about something, and then I wasn't careful about it. How many times has that happened? This should be dz dy. Okay, so now, what is the inner integral? So this is y is equal to 0 to 1. The next one is z equals 0 to 2 y squared z. Now the inner integral, this is the integral from x is equal to minus 3 to 1 to 3 of x cubed. So the antiderivative is going to be 1/4 times 3 to the power of 4 minus 1 to the power of 4. That's 80. Okay. This is equal to 20 times the integral y equals 0 to 1. Now we have the integral. The inner integral is now z is equal to 0 to 2. It's y squared z, but I can factor out the y squared z dz dy. Okay. The antiderivative of z is z squared over 2. So I'm going to go ahead and factor out the 1/2 and divide the 20 to get a 10. This is the integral y is equal to 0 to 1 y squared. And this is going to be equal to 4 because z squared goes from 0 to 2. So this is 4 dy. And this is going to be 40. Now the antiderivative of y squared is y cubed over 3. So let me divide by 3, and we're going to go from y is equal to 0 to y is equal to 1. So this is the final answer, 40 over 3. Okay, and let me just observe that if you were to divide 160 by 4, you would get 40. And if you divide 12 by 4, you get 3. And so this is equal to 160 over 12. Or equivalently, if you multiply 40 over 3 by 4 over 4, you get 160 over 12. So if you, in other words, these two fractions are the same. That's all I'm saying. Okay, and again, this is an illustration of Loopiness theorem. Loopiness theorem says that you can also, just like with 2 integrals, you can switch the order of integration. With 3 integrals, you can also switch the order of integration. Now, it's true in more general settings, but this is the Loopiness theorem that we know now, and we'll learn more Loopiness theorems later.